Okay, so we'll continue our irrigation economics lecture and our chapter, and this one will focus on engineering economic analysis. So we'll look at the decision-making process in purchasing new systems. And in engineering economic analysis, all the present and future costs are converted to present value at the required rate of return. And if the present value is positive, then the decision is made to invest in the project. So it's pretty simple. And then at the end we'll talk about principles associated with selling or designing irrigation systems. And like I said, we'll be doing that irrigation play. So engineering economic analysis combines present, which would be the capital investment here in this cash flow diagram. So we have a negative $2,500. And then future costs. So each of these represents a year. And I have the water cost, energy cost, and labor cost for each year, and then the crop benefit for each year. And the reason they're changing is there's inflation and there's different crops. So as you know, farmers do a crop rotation generally. They don't just plant the same crop every year. So there might be diseases or other problems. So conversion to a pressurized system might result in lower water costs and greater crop yield, but it might also have higher energy and capital costs. So we'll do the engineering economic analysis to decide whether it's worth investing in that pressurized system. Okay, so let's just do some basic economic calculations. The required rate of return is the interest that a company expects to earn on investments. For example, if you had $10,000, then you could buy a CD at your bank for $10,000 with a 5% interest rate. Do you guys know about that? I mean, I wouldn't know about it in college because I didn't have any money. Actually, I finally have money in my bank account because my last daughter graduated from college. So I have to think about that now. I'd never even heard about it before this year. My brother-in-law told me about it. So anyway, if you could get 5% at the bank, it would be unwise to invest your money in any project where you would expect to get less than 5%, because your 5% is for sure is insured. So in the jargon of engineering economic analysis, your required rate of return is 5%. And what you do is you convert all your future values to present value at the required rate of return, and you compare that to the cost. And if your net present value is greater than 0, then you decide to invest in the project because you've already incorporated your required rate of return into the calculation. Yes, Sitlali? Okay, I think the next 2 slides will explain how to discount things to the present value and how to convert present value to future value and future value to present value. So for example, example 2.6, $1 becomes $1.34 in 5 years if you make 6% per year. So what you would do is you would multiply $1 times 1 plus 0.06 to the 5th power, because each year you're compounding it, and it would become $1.34. Now, in answer to Lali's question, if you had $1.34 and you got it in 5 years, that would only be worth $1 in present value. So when we're converting everything to present value, we're discounting future money by the interest rate we could earn between now and then. So here's the equation to convert present to future value. So this is the opposite of what I just talked about, where we're discounting things to the present value. Now we're converting present value to future value. So either way. Okay, so what I'd like you to do is get out your spreadsheet, either get a new spreadsheet or download the class spreadsheet and make a page where what I did is do you guys know how to name cells? Yeah, so I named my cells, and then in cell C5, I have my future value. Actually, in cell C5, I have my future value equation here. In cell C6, I have my future value function from the financial column under formulas, okay? So you can find the future value function there, and then you can use it, and it has a dialog box that you can enter your values into. But when you click return, this will be what'll show up in your cell. So there's all sorts of these financial functions in Excel, two of which we'll use today. One of them is this one, where these defined functions have positions, and that's where you put your, in this case, my interest rate, which is 6% or 0.06, the number of years, which is 5, and my present value that I'm investing. And then these numbers here, 1 or 2, I couldn't figure out what they were doing, to tell you the truth. But anyway, it's not necessary. Okay, so go ahead and open your spreadsheet and calculate the future value with this function or equation, and then also use this future value function. So I'll give you a few minutes to do that, and we'll pause the video. All right, well, we'll start the video again. And here's example 2.7. So in this case, we are discounting back to the present value. And so for this example, we invest $2,000 now, and we receive $500 per year for 5 years, beginning 1 year from now. And so this is the mathematics for the calculation down here, where for the first year's payment, we divide by 1 plus 0.06 to the first. So that discounts it back to the present value. For the second year's payment, we divide by 1 plus 0.06 to the second, and so on. And then to calculate the present value, the net present value, we subtract the 2,000 investment at the end of the problem. Okay, and so so the total is $106. So would we invest in the project?
No.
Why not?
Because it's less than $1.34.
$106 is less than one.
$106.
Even if it was $1.06, even if it was 6 cents, you would invest in the project, because you've already discounted the money at your required rate of return. So for us, where the max we could maybe get is 5% at the bank, if we could invest somewhere else and get 6%, we would do it. Okay. Now here's the present value formula. So you can go to the same financial calculations. Actually, this is the future value one, but you could go scroll down to present value, put in your rate, your number of periods, and your payment, and then it would calculate the this value for you, which is back here is 2,106 for those 5 payments. Okay, what I'd like you to do now is calculate whether it's worth investing in the project at an 8% required rate of return. That's a more typical required rate of return for companies, 8%. So go ahead and redo the problem at 8%. Okay, so I'll start the video again. What'd you say, Ben? You got negative? So what's your decision? Right, so if your required rate of return was 8%, you wouldn't invest in the project. Great. All right, so we typically prepare a 20-year analysis for an irrigation system. And one reason is that that is considered the lifespan of many of the components, such as PVC pipes. The second reason is that it is a typical length of time for engineering economic analysis. And several parameters are included in engineering economic analysis of irrigation systems. So the benefit is the crop yield, or possibly it is just the improvement in crop yield if you're replacing one irrigation system with another. So you already have an irrigation system, possibly, you're putting a new one in. So what you're concerned about is the difference. The initial cost is the capital investment, which is what you pay to install the project. And some of the components do not last 20 years. For example, drip tubing might need to be replaced every few years. So that would be component replacement. However, I'd like to say that Howard Works, last I heard, his tubing had been in the ground for 20 years. It's probably been 30 years now. So if the farmer's very careful with their tubing and it has relatively thick walls, it'll last for a long time. We already discussed the energy, water, and environment cost. Lastly, there might be salvage value, but that probably wouldn't be the case with the irrigation systems. So for some economic analysis, you would include salvage value, but not for irrigation systems. Okay, so this list is from the NRCS, and it gives the expected life and the annual maintenance cost as a function of capital cost for different irrigation systems. So you can see here that they're listed lifespan of PVC pipe, buried thermoplastic pipe, is 25 plus years. So if you were doing an economic analysis, you wouldn't replace the pipe. But flexible thin wall drip tubing might be replaced every 1 to 5 years. So in your 20-year analysis, you would replace, you'd have a line item there for replacing the drip tubing every few years, however long you think it would last. So this is just a general guide, but a lot of it depends on the maintenance of the farmer, how much maintenance he's doing on his system, how well he's taking care of it. And they also have a column here for annual maintenance as a percentage of the capital cost. So for example, if you spent $1,000 on a hand move system, you could expect to spend maybe $2 per year on replacement costs. That would be things like gas or maintenance costs. That would be things like labor or gaskets or things like that. So as we've experienced the last few years, prices don't remain the same. So a problem occurs if costs increase, but the value of the crop remains the same, which seems to be the complaint of many farmers. So example 2.8 evaluates the present value with inflation and without inflation for growing alfalfa. And we're just going to look at the 6th year profit. Okay. So let me just read it. Determine the present value of the income from alfalfa 6 years from now at a required rate of return of 7%. Assume no inflation for the first case, and then assume inflation of costs of 5% per year and no inflation in the selling price of alfalfa. The present value of alfalfa production is $631 per acre per year, and operating expenses are $321. So if we look at the 6th year value, then without inflation, it would be 631 minus 321, and then we would discount it for the 7 years or the 6 years at 7% interest rate. So the value would be $207. But if our costs went up 5% a year, such that they were $430 an acre, then we'd have 631 minus 430 equals $201 per acre, or 201 discounted at 7% interest rate to $134 an acre. So you can see that even though you might do an economic analysis, if inflation changes, costs change, you know, that can completely throw it off. Okay, so now we're going to move on to the energy calculation, so the cost of energy. And first, it's easy to confuse power and energy. What is power? Yes, Michael?
Is it energy per unit time?
Yeah, it's the rate of energy use. So what would kilowatt hours be? Would that be energy or power? No, energy.
Kilowatt hour per hour power. Watt is power, so I don't know what.
Yeah, watt is power. The energy company charges you by kilowatt hours. They don't charge you by power. That's just your instantaneous use rate at any time. They charge you by energy. So that's kilowatts times time. And so the price of a kilowatt hour is generally around 10 cents. So that's what we'll be calculating, the kilowatt hours of energy that we're using. So there's different ways to calculate power. You could calculate flow rate times pressure, or you could calculate times time, or you could calculate volume times pressure. And as you might remember from the Bernoulli equation, we can express pressure as height, right? As meters. So that's the way we're going to do it. And so in this equation, where this is the fundamental equation, volume times rho, the density times gravity times height over efficiency, where volume is the irrigation depth, I, times the area of the field. We're going to convert that to this equation. So if we do all the unit conversions, the energy in joules per hectare, so joules is energy, it's watt times seconds. If we multiply 98,000 times the depth we're applying to the field, times the pressure that we're adding with the pump, divide by the efficiency of the pump as a fraction, that'll give us our energy in joules. But what we're really interested in is kilowatt hours, because that's how we're charged. So that would be 0.0272 times the depth applied to the field in a year. So we're calculating our annual energy times the energy we're adding with a pump in meters divided by the efficiency. Okay. So in example 2.9, we'll calculate the cost of energy to pump water for surface irrigation of cotton for 200 hectares of land with an irrigation system that requires 3 meters pressure head. So we're adding 3 meters pressure to the water, whether it's pumping up from a pond that's below the water surface to the elevation of the ground, or we're putting in a pipe where we need 3 meters of pressure. We're adding 3 meters head to the water, and the pump operates at 70% efficiency. So the cost of energy is 10 cents per kilowatt hour. And we'll assume in this case that the surface irrigation system water application efficiency is 65%. So we have two efficiencies we're concerned with. One is the efficiency of the pump adding power to the water, and one is the efficiency of adding water to the field. So cotton, as we might have calculated last time, or in this case, requires 91 centimeters of water per year. That's the depth of water. But the irrigation system is only 65% efficient. So we're going to add 1,400 millimeters of water to the field per year. So then we put in our energy equation, 0.0272 times 1,400 millimeters times 3 meters head divided by 0.70, or 163 kilowatt hours per hectare. And then what's the cost that we're going to spend? It's 163 kilowatt hours per hectare times 10 cents per kilowatt hour, or $16.30. And we have 200 hectares, so that's going to be $3,200 per year to pump water for that farm. Any questions? All right. Okay, so this is a long problem where we'll start to consider annual costs and benefits. And we're first going to look at a problem where a farmer is converting from surface to center pivot irrigation in the United States. And then we'll look at a same problem in a developing country. So a farmer is considering converting his sloping furrow surface irrigation system to a new center pivot irrigation system for alfalfa. And the installation cost for the new system is $2,000 per hectare should the farmer install center pivots. So for energy, the center pivot irrigation system will require 20 meters pressure head. Alfalfa requires 150 centimeters per year. That's depth, 1.5 meters, with a center pivot system. The cost of energy is 10 cents per kilowatt hour. Pumping efficiency is 80%. And no pumping is required for the surface irrigation system, which is typical because in most areas, the canals are higher than the land. So they'll take the water off of a river upstream and they'll keep the canal elevation, they'll try to hug the higher elevation so that the farmers can take the water by gravity from the canal system. Okay, let's look at water. Annual cost drops from $250 per hectare with a surface system to $200 per hectare with a pivot system, just because you're using less water. Okay, labor. One irrigator who makes $250 or $25,000 per year is usually required for every 100 acres. And I wrote this like 6 or 10 years ago, so it's gone up, I'm sure. So if you have a 400-acre farm, you need 4 irrigators full time. So that's a lot of money. So that works out to approximately $625 per hectare. And assume that yearly labor cost for a pivot irrigation system is $200 per hectare. So it's much lower. Environmental cost drops, let's just say, I mean, the farmer doesn't probably consider this, but let's say he's dumping sediment into a river. Environmental cost drops from $100 per hectare for surface irrigation due to surface runoff to $0 per hectare with pressurized. Economics, the required rate of return is 8%. The project is 20 years. Maintenance cost of the pivot and surface irrigation systems is the same. And the yield increases from $630 per hectare to $760 per hectare. So here's our energy cost. We had no energy required for the surface irrigation system. So at 20 meters head, so it has to be pressurized, and 1,500 millimeters of water, 80% efficiency pump, we're using 1,020 kilowatt hours per hectare. And then the dollars per hectare would be the 1,020 times 10 cents per kilowatt hour, or $102 per hectare. So then we can set up this table where we're looking at the change. Remember I said we're looking at the change because we're just replacing the surface system with a pivot system. So we increase our yield income by $120 per hectare. Our labor costs Actually, that should be a minus there, minus $425 instead of plus. And this is really true. I talked to a guy who had 400 acres. He had 4 irrigators. And he said that when he was surface irrigating, he would spend about 13 hours per day managing his farm. And he'd pay 4 people to irrigate, year round. So that was like $25,000 per person. And when he bought center pivots, he was able to lay off all the irrigators, and he only worked 6 hours per day and golfed the rest of the day. So it really made a big difference in his economic situation and his life, quality of life. Okay. Water cost. Oh, I'm sorry. This is a plus. Yeah. This is the plus due to changing. You increase your money by 425. So your yield goes up. You don't spend as much, so your labor costs, in a sense, go up. Everything's positive. Your water cost, you have an increase because you're using less water. Your environmental cost has an increase because you're not polluting as much. Your energy is minus because you're using energy, whereas you weren't before. And the change is $593 per hectare. So the present value of benefits is $5,822. You subtract the capital cost of $2,000. So it's an easy decision to go ahead and buy the center pivot. One complicating factor in Arizona, especially, is a lot of ground is leased. So people aren't going to invest in a system if they're just leasing ground because they don't know how long they'll be farming there. So that's one thing that would prevent people from just making this simple calculation. Okay, now let's look at the same problem in a developing country. So instead of making 35,000, well, I'm thinking maybe they make 35,000 now. But instead of making $25,000 or $35,000 per year, they pay the irrigators $2,000 per year, or maybe less. So then your labor costs hardly change. So the total change is only $123 per hectare. So then if your annual benefits are $123 per hectare, the present value of your annual benefits would only be $1,200 per hectare, which is far less than the cost of the irrigation system. So, let's go back. So then you wouldn't invest in a center pivot irrigation system if you're in a developing country. Any comments? Okay. And just one other thing, 20 years, 8% is sort of a typical lifespan and interest rate. And you can see that it's 20 years of payments at that rate is basically 10 times the annual amount. Okay. So $123 per hectare annually. The present value of that is $1,200. Okay. So let's move on to a cash flow diagram. And a cash flow diagram can integrate all the complexities of annual changes in crops, replacement of components, changes in cost due to inflation. So there are some very complicated economic formulas. Maybe you learn them in SIE 265. But the other way to do it is just to do it in a spreadsheet, where you discount everything based on which year it is. And so that's how I prefer to set it up. So an agricultural cash flow diagram has to have a crop rotation. And in this case, there are salt tolerant crops in the first year because desert soils are salty, and the first year you break them out for agriculture. you have to leach the salt out. And so you need salt tolerant crops. So these are 2 salt tolerant crops. And then you can start planting your higher value crops after that. So, so this is our crop rotation. And go ahead and download the spreadsheet if you haven't already, and go to the, I think it's called the cash flow page, cash flow diagram page. So we include inflation and required rate of return in this spreadsheet. So all the baseline costs, the present costs are here, or the present value of the yield, annual yield are here in column C. The inflation rate per year is here. And I'm going to have you adjust this back to match the example. These are different inflation rates. Okay. So in one sense, the sheet is complex, but in another sense, it's simple. Where, for example, if we're calculating the water cost in year 2, we would just use the water cost in the first now, and we would add the rate of inflation to 1, and then we would take it to the inflation rate. And that's just in every cell. So the cells refer to the year, and then the inflation rate and the cost. And notice I have dollar signs next to the inflation rate and cost. And then I do not have a dollar sign next to the year. So this way it increases the water cost every year by the inflation rate. Okay. So then the sum of the annual costs are discounted back to the present value in columns K and L. So over here. So now I have the annual water, crop benefit, energy, and labor costs. So everything's in year 1. And then I have the sum of all those annual costs and benefits in K. And then the present value of that would be discounting that back to the present value based on the rate of return 8%. And you can see that for column L12, I take K12 divided by 1 plus the rate of return, or 1 plus the year, 1 plus the rate of the return to the year in column A. So then everything, it's increased by inflation here, and then I discount it back to present value here. And I have the sum of the present values at the bottom of column L, and that's also in column G. So the net present value is $656. So would we do the project? Okay, so now I'd like you to get your spreadsheet out and change it to the numbers in the problem statement, and see if you get the net present value that is there. I think it's $323. So I'll pause the video. Okay, so I'll start the video again. So I was an irrigation salesperson, I guess you could say. And there's 2 things the farmer wants to know. He wants to know the flow rate, and he wants to know the horsepower of the pump. So the worst thing to do is just stand there and say you don't know. It's very easy to know. So you just would memorize these 2 equations, where in my area, flow rate was 7 gallons per minute per acre. And that was due to the evapotranspiration rate in Washington State, Eastern Washington. Around here, you might say 10 gallons per minute per acre would be the flow rate that you tell them. So if you had 200 acres, it's 10 gallons per minute per acre, you'd say, well, you need 2,000 gallons per minute. And then the pump horsepower is for English units is gallons per minute times feet of head over 3960 times efficiency. So it's good to memorize those two equations. And so what I'd like you to do is develop a rule of thumb for pump flow rate requirement for a region that has max ET equals 10 millimeters per day, and assume system water application efficiency is 80% and there's 10% downtime. So go ahead and calculate a pump flow rate with those parameters. And these are just some examples of how to develop these rules of thumb. So take a few minutes and do that. So the reason you design it for the maximum ET is the farmer needs to keep up with the evapotranspiration rate in the middle of the summer. And then the rest of the year, he can just use the irrigation system less. But the only thing you're concerned about when you calculate an irrigation system flow rate is the maximum rate that the farmer is going to need to use the water. Okay, did anybody come up with a rule of thumb? What would be the simplest way to do it? How about just multiply 9.65 times 10 over 13? Since I already did it for 13 here, what would that be? So in Arizona, we might tell him 10 gallons per minute per acre, but what would you tell him or her in a state where the evapotranspiration rate was 10 millimeters per day? Oh, and we also have to consider the 80% and the 10%, right? Okay, so let's just do the calculation here. We have 9.65. So equals 9.65 times 10 over 13 divided by 0.8, because I can't remember what that efficiency was. And there's 10% downtime, right? So then we divide by 0.9. So your rule of thumb might be 10.3 gallons per minute per acre. Okay. Well, now we're going to incorporate that information into the irrigation play. So let's see. I guess we need a substitute for Jeff. So anybody want to be Mr. McGillicuddy? How about Joseph? Ben? Okay, and who is Josephine? Who did we decide?
Jeff.
Huh?
Oh, I
Okay, come on up here and we'll go ahead and have our play. Guess you guys can both stand up. Okay, so I'll start. And Ben, you have to stand sort of close to the mic.
Okay, sounds good.
Alright.
I guess I can see it right there.
So I'll just introduce, we have Josephine and Mr. McGillicuddy here. Josephine, the irrigation skills engineer from Irrigation Systems Design Company. Oh, I need to narrate it here. Alright. I'm not very good at plays myself. Okay. Josephine, the irrigation sales engineer from Irrigation Systems Design Company, drives up to McGillicuddy Wellington Growing and Harvesting Farms, MWGH Farms, or My Way or Get Back to the Highway Farms, in her Chevrolet S10 pickup truck.
So Josephine, come on in, have a cup of coffee.
Don't mind if I do, Mr. McGillicuddy.
Good pronunciation. Josephine, what size pump do I need if I want to convert my section of land, 640 acres, to drip? It's really yeah.
I can see that you are growing cotton and alfalfa. So, Mr. McGillicuddy, you would need somewhere between 6,000 and 7,000 gallons per minute.
Oh, seems like a lot. How much is that in cubic feet per second?
Mr. McGillicuddy, 450 gallons per minute equals about 1 cubic foot per second. So that would be approximately 8 cubic feet per second.
You don't have to keep saying my name. It's okay. No problem. We just use quite a bit more than that for our current flood system. I'm worried about bringing electrical power out for the pump. What horsepower pump would that require?
If you want to irrigate 640 acres with drip irrigation, then you would probably need to generate about 30 psi pressure. Large pumps probably have an 80% electrical efficiency.
She then puts her coffee down, pulls out her calculator, and makes the following calculation. 30 psi times 2.31 equals 70 feet. And you have to push the button.
Okay. Mr.
Josephine puts her cup of coffee down and says,
Mr. McGillicuddy, you need 150 HP.
What's that in kilowatts?
That would be about 110 kilowatts.
That sounds reasonable. How soon can you design the system?
I'll get back to you in a few weeks.
Guys, if you don't make it in engineering, you know where you stick. Okay, so we'll spend the rest of the time